Thank you, Chris, for that introduction. So I'm Vijay from UNSW, Craig Russell, my colleague from Data 61. We are also co-founders of the ANZ SDN Alliance, and we really are passionate about that technology and would encourage all of you to, participate in the meetups and the likes. We are doing one next week in Sydney, by the way. So this talk is about network security. So thanks, Chris, for setting the scene with all those scary stories. So I'm a researcher, academic. May I ask how many academics or researchers are in this room? Not a single hand. Oh, well, a couple of them, okay. That's because most of my esteemed colleagues are actually doing what their KPIs say, write papers, do research in the lab, and all that kind of good stuff. We are trying our best. We are very excited about the field. I mean, lots of interesting attacks coming on every day, lots of new devices in the world, IoT, lots of new technologies, SDN, AI. We love playing in all that, and we do a lot of that in our lab. We write papers about it, but I do lament the fact that we really struggle to get it out of the lab and put it into the real world, and that is a major pain point for us. If we do get it out of the lab, eventually, usually it goes to some vendor who then packages the whole thing into their appliance and sells it back to us at an inflated price. A bit like the publication thing where we write the paper, we review the paper, we do everything, and then we pay to access that paper back again. So it's an interesting business model. Nevertheless, we strongly believe a fresh approach is needed to really break this cycle. And there may be some reasons why you might also want to listen, and cybersecurity is a major one. We heard things like 100 gig being mentioned today, so I'd be quite eager to know if you already have a good solution in place for your 100 gig internet connection. That's probably coming to your university at some point soon. And also, if you do manage to get an appliance, you might want to ask the question, does it really have the best of breed defense against all the threats? The threats are many fold out there, hundreds, if not thousands of threats. Do you actually have the best of breed algorithms in there to protect you against those kind of threats?
And the threats are changing all the time as well.
Exactly. And anecdotal evidence, I've talked to a few people who operate networks where we have seen certain things, and I asked them, so didn't your appliance catch it? They say, well, it can, but we turn the feature off. And like, why is that? Well, the performance really falls when you turn those features on, so we try to keep as little features on as possible so we get the throughput, otherwise packets don't go through. That's a pretty shocking state. That's my opinion. Maybe I'm biased one way. And also I've heard stories where the information that's coming out of these appliances is fairly complex, difficult to understand, too many logs, too many alarms. After a while, you just ignore the whole thing and move on with your business unless something really bad happens and somebody calls you and says something's broken. So we really feel that there should be a better way to address this whole thing rather than compared to the state of what things are today. So what we are hoping we can try to do is to together think of a way to break this cycle and actually do some innovation in a way that's flexible, scalable, and low cost. And that's what Project Nozzle is. So I would, at this point, like to acknowledge the entities that have actually funded this project over the last year, among them being Google, was one of the initial entities to fund us. DST Group, Defense, has been funding us, and AARNet this year. So thanks again for that funding. But I think this is just the beginning of the journey. We have a long way to go. So our approach in this project is really to leverage commodity switching hardware, SDN hardware, because it's getting really cheap, it's very generic. I mean, the SDN paradigm, for those of you who don't know, is a very simple abstraction of the switch. It's not a layer 2 switch, it's not a layer 3 router, it is a switch that gives you a match and action capability. You can match on anything in the packet header, and you can take any action, such as forward, drop, copy, edit certain fields, and so on, and rewrite, and so on. So it's an extremely generic paradigm of a forwarding element. And that generic paradigm allows us to build a whole diverse set of applications on top, and Nozzle is just one of them. And these things are getting pretty attractive from a price point of view. And I can mention some numbers, but you can get a 400 gigabits per second, 200 gig ports and 20 10 gig ports appliance for about $30K. A 6.4 terabits per second one is already in the market. Arista launched it just last 2 weeks back based on the Tofino Barefoot chip, which is fully programmable. So amazing stuff is happening there. The price is really coming down. And then combining it with commodity compute servers, which are getting very powerful, which are getting much cheaper, and you're not locked into any particular vendor.
So I'll just jump in and elaborate that point, Chris was making the point about a lot of those security threats. Detecting security threats is a very compute-intensive process. So typical security appliance that's a fixed box has got a fixed CPU with a fixed number of cores and a fixed amount of memory. So it's not scalable. It might do what it does very well, but when a new threat comes along that requires a different algorithm to detect it, it just doesn't scale. The beauty of commodity server class compute is that it can scale elastically. So you can have as many compute servers as required to run that particular algorithm to detect that threat. And that's a thing to do off box, right, in a server class compute, not in the packet forwarding element.
And I'll add a bit more to that, that even though servers are getting fast and cheap, you still don't want to put all your switching and routing onto just commodity servers. You would not throw away your border routers or your switches and replace them with servers. So even though NFV, which you might have heard of, network functions virtualization, is being talked about as moving everything into compute, reality is if you want to do 100 gig or even 10 gig, just putting servers is not going to be good enough. You do need a combination of switches and servers, each to do the thing that it's best at. And that's what we'll shortly look at.
Switches switch well, servers compute well.
Exactly.
So not vice versa.
Right. So the objective in this project is really to build a platform for cybersecurity solutions that gives you that scalability, so you can expand it modularly based on these commodity components. It's very flexible, so you can use the best of breed, both hardware and software and AI algorithms. Because in the research literature, literally every day, every week, we are seeing publications coming out how they're doing some really novel ways of detecting attacks and mitigating them. But reality is they will never get translated to the real world because there is no platform to put it on unless you convince a vendor to embed it in their appliance and then sell it back at an inflated price. And we want to do this as a low-cost solution. So what we'll look at is how we bring together software-defined networking, or SDN, to build the workers that extract attributes. And then build the inference engines based on AI that actually make sense of these attributes. It's a bit, think of going to a hospital, right? You get a full service. You go in, you get your temperature and weight and all that taken. You go get a blood test taken in the pathology. You go to radiology, get an X-ray taken. And then the specialist walks into the room and gives you all of 3 minutes, looks at your reports, makes a diagnosis, walks off. So that specialist time is precious. They don't sit there taking your blood and taking your X-ray. That's done by a set of workers. And that's what we're saying. SDN does that really well. At 100 gig traffic, you have literally a few nanoseconds per packet. What SDN can do is forward those at line speed and extract those attributes for you and condense the information, so then you can use really sophisticated algorithms on top that just look at these symptoms and make the right inferences. So let's actually look at what the architecture could be. And by the way, this is something we have built. We drink our own Kool-Aid, and we are using it on our campus, both of our networks, and it works. So let's start from the very bottom. So imagine an appliance that's actually sitting between the internet and your enterprise. Today, what you'd buy is that full gray box from your favorite firewall vendor. But let's look inside what actually happens in there. So at the bottom, we put the SDN switch, which is just letting the packets go through. So we put a rule in the beginning saying match star everything, forward it on, but also send a copy up to my servers, right? To the workers that are sitting up there. And then the compute server is actually keeping a little bit of state. And it's saying, well, if I'm seeing packets for a flow for a while, it's a long flow. Let me go back and punt an entry into the hardware to stop seeing any further packets of this flow. Because, hey, I know it's a Netflix flow. It's going to go on for an hour. Somebody's watching a movie.
It's a data transfer like the Science DMZ example, right?
Exactly. Or it could be a long...
The thing that the graph we had earlier about the difference between a commercial network, they had that highly periodic behavior, and the AARNet network had that big burst, and I think Chris said, that's one user doing one big transfer. Does that transfer need to go through a firewall device? Absolutely not. Why look at every packet when you know it's safe, you know where it's going? Punt it off to hardware. Yeah, exactly. So in other words, bypass it. And that's exactly what the SDN switch is letting you do here. It's letting you bypass those long flow traffic in your hardware, keep it in hardware, don't hit the software with this, because you know what's happening, you don't want to see any more packets. And we have done this both in our own campus networks and also in a tier 1 carrier, because we are actually in trials.
And we have published papers about it, and we are not the only ones. Many other papers in the literature have confirmed that about 3/4 of the traffic on a typical network is carried in the top 1% of flows. Those are the long flows. Could be science transfers in your case. It's often Netflix and YouTube and the rest, or Twitch, a lot of it in general carrier networks. So once you've suppressed those long flows, the attributes are extracted by the workers, and we'll soon talk about what attributes are, but things like, what is happening in DNS? What is the kind of signaling traffic, be it, SNMP or SSDP or whatever it is, or SIP? What about, the number of connection requests that are happening, and so on and so forth, which we'll briefly look at. But all this information that's collected by these workers is then posted into a messaging system. So anybody who wants to listen in can listen and do whatever they want with it. And that's why we've put a dotted line there, which means that the system below that messaging is what we are building and we will support. The system above is where we encourage everybody to chip in and say, look, I want to build my own inference engine because there's a new kind of attack. I want to detect it, and I need these symptoms because I'm diagnosing that kind of disease. So you just subscribe to the appropriate channels on the messaging, you extract those attributes or symptoms, and make the diagnosis that you want. Or you could even start simple. You could just take what's coming on the messaging, just put it into a log, because for heaven's sake, next month I want to know what happened last month in my network, and this is a simple way where you just store the symptoms or the attributes rather than the full packet traces. Or you could build a user interface on top that takes these attributes and symptoms and displays them in a nice way so you can customize it to the way you want to absorb that information. So a whole range of possibilities open up on top, which we'll walk through a couple of use cases very soon. So examples of some of the attributes, and today we'll focus on a couple of use cases. One is around DNS. When we did this, we said, let's just extract DNS to start with. It's simple, it's 0.1% of the traffic, and yet it has a lot of information. Let's see if you can make use of that, and we'll see some of the results from that. But in general, you can compute host-specific attributes, how many TCP connections are ongoing, how many requests are coming in, what are the volumes, on a secondly, minutely, hourly, daily basis. You could extract the flow attributes. What is the length of the flow? Is it talking to servers in China or some other place? What are the cipher suites being used? You could even go and look within the flow. What is the distribution of packets? What are the gaps between them? What are the sizes of the packets? And a lot of other signaling information. Now, this is just, I'm not saying we have implemented all these features. We have some of them, these attributes. But we are already starting to put them to good use, which is giving us fairly interesting insights, which we'll look at very soon. So let's start by looking at DNS in particular. In terms of volume of traffic, it's less than 0.1% of your network traffic. Or
at least that's what we discovered at UNSW campus and CSIRO's.
Yeah, fairly consistently.
Yeah. Reasonably.
The other thing with DNS is often they are configured to pass through a firewall because it's fairly critical to operations. And that can create a few issues, as we'll see very soon. It does expose a wealth of information. It exposes what are your resolvers? Who are the entities within your enterprise that are making the DNS queries outside, largely? What are your name servers? Who are the entities within your campus that are actually answering to responses coming from outside? What are your public-facing web servers, because they are being queried for? And what are your regular clients that are making regular queries outside? And DNS is used for DOS attacks. Web servers can be brought down by a DNS amplification attack directed at them. We have seen evidence of exfiltration, data being put into DNS queries and sent out of the campus, out of the enterprise, because, hey, it passes through the firewalls. And of course, reflection and amplification attacks, where we have seen resolvers that are being queried with a spoofed address, so the responses are actually going and hitting a victim pretty heavily. So the DNS worker in Nozzle, we have implemented in actually a couple of ways. One is just putting a flow rule saying, UDP port 53, send a copy, and a worker will look at it. We've also used the DPDK framework in conjunction with Rust and Golang, and he's the expert on that, and the developer, Himal, is sitting at the back, who can answer all the detailed questions around it. But we are quite effectively and very easily able to gather this information, push it on our messaging channels. And for what I'm encouraging you to do is to try to build the entities that sit on top of the messaging, ingest this information, and make some sense of it as you want. We got a student to do it. It took about a week or so. to write some simple code, be it in Go, Python. NATS supports clients in any language you want. Pick your favorite language, write a client. It's seriously less than 50 lines of code. You will get those messages coming into your code. You can then, and it's all packaged, by the way, so you're not getting raw DNS packets. The workers are actually aggregating, and every 1 second telling you all the DNS that's happening on the network. And once you ingest this, you can do whatever you want with it. So we got our students say, that was quick, you did it within a week, spend another week. So the students spent another week, just looked at how many ingoing queries, outgoing queries, incoming responses on a per client basis within our campus. And we have, about 50, 60,000 students and staff and so on. Looked at the number of external servers contacted, what were the number of external clients querying inside us, what is the fraction of time things were active, and put it into a vanilla classifier, right? A standard clustering algorithm that's built into any, scikit or Weka machine learning things. So he didn't know a thing about machine learning really. He just called a library. That's it, with these attributes. And the thing clustered it for him and gave him back a response saying, we think you have 40 DNS name servers, 14 resolvers, and a bunch of public servers. Actually, it's 500 plus, not 5,000. Sorry for that. So we said, really? Let's go and confirm that. And sure enough, we took it to our IT, and so did Craig to his IT. And yes, it does turn out that actually those were the name servers and those were the resolvers. So it actually took fairly little effort to map out what our enterprise looks like from the outside in terms of resolvers, name servers, public-facing servers, and regular clients. And sure enough, there was some evidence of some activity that did not look quite right. So we then went and asked our respective ITs, like, what's happening with these ones? We're getting these reflections attacks happening. They're being queried from outside. And the response we got was, yeah, well, that's actually not managed by us. That happens to be an on-site retailer to whom we provide the network service, and security for their stuff is their problem, and that's the way they have configured it. It's fairly open. Obviously, they don't know what they're doing or something like that. So the point being that it actually didn't take a lot of effort to find these things by a student within a few weeks once the platform was in place. And that's the point we want to emphasize, that we've been working in SDN for 4 or 5 years. We have tried every controller under the sun. We have tried lots of combinations of open source. Many of them don't work. Some of them work. We have got that combination together somehow, working in a reasonably good and stable manner. And as I said, some of this is in trials with a carrier, to the point where we are fairly confident our platform can give you those attributes at line speed. Right? We are only working at 10 gig today simply because nobody's giving us a 100 gig traffic stream. But our switches have those 100 gig ports that are pretty empty. On our current switch, which has these 22 ports, we're actually using 4 ports. And by the way, all this is done with 4 cores. So we have a blade server, we're actually using just 1 blade on it, right? So that's how
and only
scalable it is.
4 out of the 16 cores.
Exactly, exactly. So I think we got some pretty good wins right away. So we did a bit more stuff with DNS, tried to look at what exfiltration was happening, and Craig will briefly talk about that.
Yeah, tomorrow I'm giving a lightning talk, and I'll talk a little bit more about this one because there's a bit of data analytics involved, but essentially this was trying to look for DNS data exfiltration, which is where a piece of malware embeds itself on a machine, does DNS lookups to a server outside the machine, so outside the campus, and in the subdomain field, it sends encrypted information that it might harvest from that machine. So typically, there's been attacks in the past where exfiltration has taken, credit card numbers and that kind of stuff that can harvest from a computer, encrypt it in the subdomain field of a DNS request. And what we were able to find fairly quickly using this technique was we could extract from the NATS channel the subdomain field, which is what I highlighted there. That's actually a Cabana interface. So we had all the DNS packets put into Elasticsearch. It was quite easy to write an API that can extract just the subdomain field, run a machine learning algorithm on the subdomain field. The subdomain field has a very high information theoretic content, which is evidence of exfiltration. You've then got a 5 tuple for that flow. You can punt a rule back into the switch and you can kill that flow. very quickly, and the machine can do it all. Doesn't require a human. So that was a very quick win.
Yep.
I'll talk some more about that tomorrow.
And just to kind of make clear, when Craig mentioned, ELQ and Cabana and so on, this is all staying on top of the NAT. So once you get information from the NAT channel, you can choose to do whatever you want to do with it. He chose to put it into ELQ and Cabana and do all this stuff. My students, one of them, what they did is they extracted a whole set of attributes: the length of the whole DNS request, the entropy in it, the number of numerical characters, the number of capital letters, the number of dots, the labels. And they also went to Alexa and did a reputation on that site. Because some sites legitimately use, like antivirus, McAfee uses a lot of long domains to encrypt some information and send it out, which is legitimate because it's a reputed domain. But CNR.io, we found, is known to be an exfiltration site, and sure enough, there was a lot of activity going on campus. Well, when I say a lot, there is activity going on campus with CNR.io.
I will add that actual trace there was me running an exfiltration myself between CSRO and UNSW, and it certainly wasn't blocked by the organisation's firewalls because they don't look for that stuff. And in fact, when I asked the guy who runs our border, I said, "Do you look for exfiltration?" He said, "No, I don't." So,
right. So the point is, I mean, the features may well be there, but some of them are either not turned on because of performance reasons or whatever else. Again, this is not meant to be any reflection on the capabilities of our IT. They are very, very competent stuff, but this is the reality of the way cybersecurity is out there. And we have techniques to mitigate it. I don't want to spend too much time, but if you look today, one of the most common techniques is black holing, which is essentially saying, if I'm under attack, I'll put a gun to my head and shoot myself. Hey, I'm not under attack anymore. Isn't that great? We think that's a pretty primitive solution. We actually have a better solution specifically for DNS-based. So if I'm getting unsolicited responses for DNS, I never ask the question and somebody's responding to me, we can drop all that. So my services are not impacted from a server point of view, right? And we think that's a more sensible solution than pointing a gun at your head. Anyway, maybe it's just me. So we went further. We said, can we use some of the other attributes and get some more information out of it? And one of the other areas we play quite a lot in is IoT. So we got a lab with 30-odd gadgets and gizmos, and students love playing it. We also, by the way, have all the VR gear. I have Samsung gear. We have Oculus Rift. We have every VR gear in the world we could get our hands on. It's all in the lab. We are doing profiles and signatures, and we're trying to look at what attacks could be possible and so on. But IoT is particularly interesting because of the diversity of devices out there. And if you look at the behavior of an IoT device on the network, there's actually a pretty clear signature. And we are showing it visually just so you can appreciate it as humans. If you look at the TP-Link camera on the left, you can see how much is local versus internet communication, what sites it talks to, what ports it uses, what protocols it uses, and what local ports it uses. So all this information you can see visually. On the right, you can see it for the Amazon Echo. And if you can see it visually, you can capture all this as attributes. And these attributes you can feed to a machine. Again, vanilla machine, we didn't do a lot of tuning. The machine was able to actually identify these devices with a 99.8% accuracy. Immediately, and by the way, everything I'm saying is validated with academic publications that are either published or under review, and I invite all of you to review them. If you think we have holes, which we well might, point them out, we'll fix them, you can fix them. But we really want to be open here with our techniques, unlike a lot of vendor stuff, which we never know what the underlying technique is. We don't know what the underlying accuracy is, so we just have to believe that what they tell us is true. And being cynical, I never do. So we applied that to the devices in our lab. And if you look at every row here is an attribute. Every column here is a device. We just did some clustering and color-coded, and sure enough, every column is unique. Every device has a unique signature, even just looking at these attributes. And as these attributes get richer and richer, you can do it even better. What all this means is, we have a technique which just looks at network behavior, and using our platform, which is extracting the attributes and running some simple clustering and classification algorithms, we can identify the assets on campus at runtime on an every hour, every day basis. So if things change, somebody installs something and they left it open by mistake or whatever happened, we can catch it immediately or very early on. It's a continuous validation of your assets. The same with IoT, which is going to be the next thing that hits us is as we start putting more webcams in campus and other gadgets and gizmos, who knows what's happening to them, who knows what's hacked. We can actually identify our own assets, and we are now building anomaly detection mechanisms which can see if a signature starts departing, it could be a symptom of an attack. So we are in the process of building all that stuff. But the beauty is whatever algorithms we now come up with, we can actually execute on our platform immediately, so we can validate if it really works in the wild or not just in the lab. So you'd probably be thinking several reasons why this can't be done. And I fully concede that, we have not solved all the problems in the world. What we are really saying is this is a platform which will actually help you experiment, help you develop the right tools and techniques to manage cybersecurity in your environment, rather than just cutting out a check to a vendor and hoping that, yes, everything's protected because, hey, I've paid a vendor to do it for me. There will be concerns because with anything innovative, it's not 100% guaranteed. So you would probably be asking several questions, might be going through your minds. Here are some that I've encountered, we have encountered in the last few months, saying, hang on, I got NetFlow, SFlow, I'm good. I don't need all this stuff. Well, you really can't mitigate with NetFlow, SFlow. You need a completely different mechanism to go back and mitigate. And there are other reasons also. What SDN gives you is a paradigm to do both. You can monitor at any granularity by adjusting your flow rules, what you want to match on, but you can also change the action and go back and mitigate. You can kill a particular flow, or you can kill a device, or you can kill a subnet. You can do whatever you want to do, really. Of course, platforms are great, but who will support it? Very good question. We are trying our best to support it to the extent we can. We really look to entities like AARNet to hopefully support us more. Google's definitely behind this. I just had a meeting day before yesterday, and they said they are actually quite happy with progress. They are now looking into giving us a further level of support for this. But I think, like Google, the whole community needs more people to be embracing an approach which is more open and more flexible and more modular, so that we can actually tackle the cybersecurity problem collectively in a better way than what we get as a bundled solution from a vendor. There might also be concerns around time and skill. Who's going to write some code to even subscribe to the NAS channel and do the inferencing? We are happy to provide templates, some of the work we have done, but really, we are providing the platform. We really want more people to be looking into the appropriate apps, and we'll try to make it as easy as possible to write an app, but ultimately you will need some skill within your organizations. But that's where I say, look, most of you are from universities. You have lots of students. Pretty much everything I'm talking about here has been built by students as a first cut, right? So if we can do it, so can you. There might be concerns that the defense we are providing is not a comprehensive solution. Hey, do we have a long list of attacks against which we can tick and say, yes, we protect, yes, we protect? No, we don't, right? Because we are building the platform. We are hoping that diversity of apps, which protects against these various attacks, comes up over time. But we provide the platform, which is a necessary prerequisite to be able to build those solutions. And of course, there'll always be some concerns, white box, untested. Am I confident that I can actually put it inline in my network? Now, that's something, because we are actually working with some carriers, we have some thoughts around, and we look for other inputs here. A first step solution could even just be to take a tap off your network, feed it to the Nozzle platform, see what insights come. Are we doing as well compared to your existing appliance? Maybe we're doing better than your current appliance. It will show you those insights. And we can even consider signaling your appliance back to mitigate, if that's the way you think you really feel comfortable adopting a solution like this. We could take this a step further, and or in a case where it's greenfield, where you suddenly get a 100 gig service and you simply don't have an appliance to put in there, you could consider making this work inline with a bypass solution. So there are devices in the market, that blue box there, which are essentially, it's an active device, and what it will do is it'll take the traffic from the left, send it through the appliance, loop it back, and then send it to the right. But the advantage is, if the appliance fails, and the appliance is responding to a heartbeat from the bypass, if it doesn't respond to the heartbeat, the bypass cuts it off and the traffic just goes through. And if you pull the plug on the active bypass, it has a fail-safe mode where passively it'll let the traffic through. So we can build these fail-safes in place so that there is a path to taking little steps till you get comfortable enough before eventually putting such a solution fully inline in your network. So anyway, we are hoping that what we've talked about today at least stimulates some thoughts in your head about what might be the approach towards cybersecurity in the longer term. Again, we are not saying here's a solution and it'll protect you today. What we are really thinking is looking, 1, 2, 3, 5 years down the track. If we don't do something today, you'll be exactly in the same situation 5 years from now, where you're forking out possibly a lot more money to your vendors to give you a cybersecurity solution. I think it really needs us to work together for us to take our ideas out of the lab, into trials, into production, and for you to work with the view that you're helping co-develop a solution that can actually be used by you in a few years. It's scalable, it's customizable, it's flexible, it's modular, it uses the best of breed. You don't like an SDN switch vendor, throw them away, buy a different switch. As long as it's a standardized interface, you're actually not locked into any vendor here. Anyway, those are our thoughts, and I really look forward to any discussion. So I've just put some price numbers because we work with some of these guys. Buying a hardware switch, as I said, a 400 gig switch today with full SDN, OpenFlow 1.4 and beyond compatibility, and it's being used by many carriers and cloud providers in the market, costs about $30K. Add in some, compute, maybe another $30K. Add in a bypass safety switch, that max 100K is your hardware cost. The rest is software. Our platform software, we are more than happy. In fact, we are wanting to give it free because we are also itching for trials, because obviously we would like that validation. And we're really looking to see if AARNet could also be involved in supporting this to the extent where we can take it into trial, especially if there are kind of 100 gig services, which is a new opportunity because you may not have an existing solution. So you want to add anything, Craig, or I think I've spoken enough?
No, you're a better speaker than me, so you've covered most of it, I think.
So with that, I think I'll stop, and thank you very much.